This is the second part of a tutorial on probabilistic dimensionality reduction. And actually, I was reviewing my slides. Even the things I wanted to get through in this part, I felt I wasn't going to. And the problem with that is that if you try and put too much in, you go too fast and it's difficult to understand. So I'm not going to do one of the things I mentioned in my abstract, which is sort of deep probabilistic models. Because I think the amount of time I need to spend on the spectral stuff, which I think is quite important, is too much for me to do that. So apologies if you sort of came specifically for that. I'll start with, broadly speaking, as I started last time, because I appreciate not everyone would have come in March, and even if you did come in March, your memory isn't probably so great. Certainly my master's students don't remember anything 1 week to the next, so I can't imagine that master's students here will remember things 7 months after. So I'll start with this sort of high-dimensional data motivating example. I'll go through it relatively quickly compared to last time, but it's on the old video if you want to see that. And then what I want to do is really flip things around from what I did last time. So last time I sort of derived dimensionality reduction algorithms by starting with models, which is the way I tend to do things in practice. But this spectral dimensionality reduction stuff, I'm going to do... I'm very keen on this separation between model and algorithm. I've not seen it really being emphasized so much by other people or even sort of mentioned at all. So I'll try and introduce these spectral approaches sort of more from an algorithmic perspective. But then what I want to do is give you a unifying probabilistic perspective on these spectral approaches, which is more of a model. So that's a flipped way from the last tutorial where I actually started by introducing dimensionality reduction as a model and then looked at the algorithm. Okay, so notation, memorize all of this now. It's more for reference if you're looking at the slides offline. The slides are on my webpage. If you look for my talks page, the top Google hit is my old talks page, the second Google hit is my new talks page, and you'll find these slides here. But just for overview, the particular important bits to remember are x is going to be latent variables. So when you see x, that's sort of unobserved, and y is always observed. Y is in the form of a design matrix. That's convention. So a design matrix is a matrix with n rows and sort of p columns, where n is that number of data and p is the number of features. So p is typically high dimensional. And what we want to do in dimensionality reduction is reduce this high dimensional object p to a low dimensional object which is q dimensional. So that's the latent dimensionality. So my grand used to say mind your p's and q's. Another thing that I'm going to use a fair amount in this lecture is the matrix of interpoint squared distances. I'm being careful to say squared distances. Probably later I'll start slipping up and calling them distances. But broadly speaking, every time you see these things, there'll be squared distances. That makes things easier because I don't have to keep putting squares in place. I just have to put the occasional square root in. So matrix of interpoint squared distances. So that's between any two given data points. It's a distance for all the matrix, and of course it's symmetric. And then K, which is a similarity matrix or a covariance matrix or a kernel. And the idea in this talk is that's all the same thing. Whatever you think you've been, here's a similarity, here's a covariance, here's a kernel matrix, it's the same thing. So, but it's an n by n one. It's not the covariance of your data across the p data points. It's the covariance across all your data points. Sort of Gaussian process covariance, or the kernel that you derive in a kernel method, or very commonly in areas like psychology, people will think of these as similarity measures. I'm going to use H as a centering matrix and B as a centered similarity. These are less important and L as Laplacian, because when they come up, we'll see them. So this is the slide I used at the beginning of the last tutorial, which is a sort of slide that I always think about when I think about data. That if I see data like that, you think it's sort of quite complex data, and then the sort of thing I then do is, you always think, mixtures of Gaussians are ways of modeling complex data. And I always, when I heard about the mixture of Gaussians, you could fit that, 20 years ago or whatever, I thought, what a cool model. Surely all our problems are over, because now we can do density model for quite complex things. What I talked about last time is a brief review of why that's not a good idea. So, the way I introduce this is considering the idea of a Gaussian egg. And in one dimension, so you've heard this before, but I just think that this is a nice visualization of this idea. It's something I put together for trying to get this across, because I heard it before, but I never really believed it. This is a Gaussian egg, so it's a Gaussian density, and then we've got the yolk of the egg is the area under the Gaussian between 1 and -1 standard deviations. The white of the egg is the sort of bit beyond, and just around the standard deviations, I've got this little green bit, which if you ever boil an egg, if you overboil the egg, I think it's iron sulfide, it makes a bad smell. It's the green bit at the interface between the white and the egg. So I've given it a little bit of volume here in one dimension. The green bit is 4.8%, and it's just either side of 1 standard deviation away from the mean. Now, the interesting thing about this is what happens as I change the volume of that. Sorry, the dimensionality of that Gaussian. So this is a 2-dimensional Gaussian now, so you're looking at it from above. So this is the core of the egg, it's sticking out as a big bump. And the sort of thing that people refer to is that actually all the mass of these Gaussians starts to concentrate in these regions here. So what I've got is, turns out you can compute that analytically, how that happens. As you go up to a 3-dimensional egg, and this is in the last lecture if you want to go through it, describing how to compute that analytically, and somehow my diagram's gone quite small. If you go from 1 to 1024 dimensions, if you increase the dimensionality of that Gaussian, and we look at these 3 different areas here, this was the situation we saw with 1D, where most of the mass was right in the center, near the mean. And this was the yolk, sort of outside the standard deviation. This is how much was on that sort of green interface. But as we increase to 1,000, and it doesn't happen, that quickly, actually. It's sort of interesting. When I first did this, I expected this to sort of drop away fairly quickly. This is 1,000 dimensions. When we get to 1,000 dimensions, all the mass is dominated by the green. But as I talked about in the last time, this is a little bit misleading. I actually use this as a straw man. I hate the focus on cursive dimensionality. I mean, this is associated with the cursive dimensionality and what happens to data. So as I asked last time, so we'll see if people remember, in practice, these things are less of a problem, because in order to do this, I have to make an assumption about this Gaussian that I'm putting together, about these dimensions. And this assumption is very rarely mentioned when people are introducing the cursive dimensionality. So I always want you to sort of remember when it applies. Does anyone know what that assumption would be across these dimensions for what I'm doing with the Gaussian in order to have this mass increase in this way? And, the consequences are more, the distances that I'll show in a moment. What assumption am I making across dimensions about my data set? Hugh got it last time, so he can't answer again. At the back. Could be, yes, but actually it's more another one. It wasn't the one I was referring to. Actually, I'm making that sort of. But it's another one, actually. Independent dimensions. Every time you look at a cursive dimensionality proof, check. They normally start with making something that's akin to an independence assumption. If you get given a data set where all your features are independent, that is kind of extraordinary. They don't really exist. I mean, unless you've specifically reduced a high dimensional data set, I should say, where everything's independent. That doesn't happen. They're correlated. And I sort of went through that last time in a bit of detail. So in particular, what I did is sort of say, well, let's not just look at what I want to see. That issue of everything sitting in the shell of this Gaussian has this other effect. And the other effect is that every point in a high dimensional space, if those dimensions are independent, is equally far from each other. So it's a sort of, you can't, if you sample independently and you think about this space, one of the consequences of all these points being on the shell is they're sort of all somehow orthogonal to each other and they're all sort of equidistant from each other. So you often hear this sort of thing said, well, in a high dimensional space, everyone, this is given as a fact, and it's such rubbish. It's not true. I mean, in a high dimensional space, yes, if you sample every dimension independently, everything is equidistant from one another. If you actually look at any real high dimensional space, and that's what I did last time and we'll do again, so this is actually showing for a 1,000-dimensional Gaussian with 100 data points. This is a histogram with the theoretical, so I derived the theoretical in the previous slide, the theoretical distribution of interpoint distances, or interpoint square distances it probably is, the theoretical distribution and the samples. So it shows that the theory is that every data point, so it's square distance, isn't it? Because it's 2. Square distance, even says square distance. I can read as well. Actually, so the points are all a square root of 2 apart if their standard deviation was 1. Everyone's square root of 2 apart. And this is actually the theoretical distribution in 1,000 dimensions, and the histogram's right there as well. But when we look at real data sets, so this is a data set that we'll look at a little bit. Simulated measurements from an oil pipeline, 12-dimensional data, and the data's, it's actually an artificial data set, although it's not quite clear when you read about it. the idea is you've got, I think, 12 probes measuring, I can't remember if they're density probes, interferometry. They're looking for reflections on these boundaries. And you're measuring them, and you've got different regimes of flow within the pipe. 12-dimensional data. So you've got 1,000 data points in this. It's called the oil data. Oh, there you go. I should have actually shown that. So they're gamma densitometry sensors arranged in a configuration around the pipeline. And then you get different readings across these sensors according to what the flow regime is. Now, if you look at this, the theory of what the interpoint distance is, this is the theoretical curve, and this is the actual curve. This is the actual histogram, sorry. So there's a mismatch, even at 12-dimensional spaces. This is another data set. This is 55 frames of a person running for 3 strides, like that. So it's the X, Y, Z coordinates, motion capture data from Ohio State University, which I tend to use a lot for dimensionality reduction. It's 102 dimensions because there's 34 points, 3 dimensions associated with each point. And if we look at it for this one, now we see the interpoint distances. And that's the theory. The theory doesn't match up. It's not like that. The actual interpoint distances, some stay close and some are further away. They're not all the same. This is why, I mean, it's not that surprising. Why do you think King Nearest Neighbors works, you know? So this one is 6,000 dimensional data with 77 data points. 6,000 dimensional data. It's an old 1998, one of the early gene expression data sets, and it's quite fun to look at. It's about yeast cell cycle. This is a DNA microarray, and it's the sort of intensity. These are each representing how much mRNA was in the original sample of particular genes. And then there's 6,000 genes, and you've got the measurements of those for 77 different experiments. That's the theory, 6,000 dimensional. Everything should be square distance of 2 apart. Actuality, nothing like it. And the explanation is, see, well, this is me. Look. That's me when I was a young lecturer. With my eyes closed. I think I had pink eye that day. This is Martin and John. I was tired. It's a very hard job being a young lecturer. Martin looks tired too. He was a professor. And this is John. John's still at Sheffield. Martin's in Spain. This is a data set they collected of speech data of vowels, and John still builds on this work for, sorry, my citations are missing. I'll recompile the slides and make sure the citations are in there. Apologies for that being missing. Of people, a visual data set alongside some vowels. It's an old data set now, but it's quite high dimensional. So it's, because we map the data itself, what we're trying to do with visualizing this data is turn it into HMMs. These HMMs have an enormous number of parameters. And actually, the HMMs that were being used for each subject, there's 24,750 parameters in the HMMs. And then I'm basically choosing a distance between subjects by the distance in that parameter space. So it was some work John and I did for Interspeech a few years ago on visualizing speech synthesis. So these are HMMs designed for synthesizing speech. So John fitted those HMMs to the corpus. And then we've got 24,000 dimensional parameters that represent each person. And now you see it's even peakier, but again, even though the distances are a bit more concentrated, they're still nothing like truth. And the reason for this, one reason for this is, well, let's look at this. This is also 1,000-dimensional data. It's an 1,000-dimensional data set that I've sampled from a Gaussian distribution. But I gave the Gaussian a particular covariance. And so the interpoint distances take that form. And we're going to see very clearly why they take that form as we go forward. Because I love this representation of data. I mean, covariance isn't the only thing, but it's a really easy thing to compute and very easy to understand. The Gaussian I sampled from is a low rank covariance. Each data point is independently sampled with this covariance here, so their features correlate. Because of that, you don't see that peaky distribution. I've got this low rank form. And this turns out to be a dimensionality reduction form. And the interesting thing about this is, in this low rank form, I've chosen this matrix W to be 1,000 dimensional by 2. So this low rank form is 1,000 by 2 by 2 by 1,000. So this thing is rank 2. And this diagonal makes sure it's a valid covariance. It adds a little bit of noise. So that is independent. So Gaussian covariance is sum. So you can think of me as sampling something that's 2-dimensional and adding noise to it across all dimensions. And now I'm computing the interpoint distance on that And surprise, surprise, that theoretical curve doesn't fit. But if I take the theoretical curve that's associated with 2 dimensions, that does fit. Because there's only 2 independent dimensions here. So actually, I did a lot of this work for teaching, and I've never taught this course because I moved university just at the moment I was about to teach it. So that taught me to always delay preparation of teaching. So I did this for teaching this sort of stuff to try and get these points across. People have asked in the past, well, can you estimate the actual intrinsic dimensionality by looking at these histograms of distances? I don't know. So I don't know the answer to that. It would be a cool thing to look at, and I keep forgetting that it would be cool to find out if that was the case. So how do we model this data? Well, again, I used this other motivating example later on in last lecture of how we should look at data. So what this is sort of saying, this motivational part here is saying, okay, fundamentally, the data is not independent across dimensions. But one thing that you can potentially do is try and find some controlling dimensions over which it is independent. It doesn't even have to be independent. You can do a dimensionality reduction in order to look at that data. It's not the only thing you can do. It's one thing you can do for dealing with high-dimensional data. But this sort of motivation is leading to that. Ooh. Another way of motivating that, which I normally use independently, but I'm going to correlate them now, is this motivating example. I'm going to use this because we're actually going to look at this as a data set in a moment. And we're going to compute squared distances, but we're not of the type we've just sort of seen. So the USPS handwritten digit data set is quite well known, and this is a 6 from that data. It's very, very high dimensional, 3,648. And that would be an independent sample from that space. And these spaces are massive when there's independence. This is why it's such a foolish assumption. It's like a needle in a haystack. You would never see that 6. You could keep sampling the size of this space. You would never see that 6. You would see a bunch of visualizations of points that are all equidistant from one another. You wouldn't see that 6 because the data set of 6s is very unlikely. It's 2 to the minus 3648. Is the probability of that 6. And this is my proof. There's a second 6. You didn't see it. Proof by MATLAB. Third 6. Okay. So in dimensionality reduction, non-linear dimensionality reduction, which we're going to move on to, but we'll start with linear, what we do is we rotate a prototype. And if we sort of say, instead of modeling that 6 as independent, what we say is, I would believe 6s are more generated by taking a 6 and rotating it around. So what I've created for the purposes of illustration, and again I went through this more detail last time, so just sort of zooming over, is a data set of rotated 6s. And what I'm showing you here is the first 2 principal components of that data. PCA is the, what's the right word? PCA is the, what's like something that's super fundamental and everything comes back to? All roads lead to Rome. It's the Rome of dimensionality reduction algorithms. It's somehow, like loads of stuff turns out to be PCA in the end because it's an odd algorithm. And last time, I actually started with a variant of PCA and generalized it in a nonlinear direction. Today we're going to look at a variant PCA, but it's a totally different model. But algorithmically, it turns out to be the same, which is why PCA is a bit weird. So PCA is always an interesting thing to do on data. And here we're looking at the first 2 principal components of this data set I've created by taking that 6 and rotating it 360 times 1 degree at a time. Now, when I first did this, I didn't know it was going to be a circle. You know, I could have speculated it might be a circle, but then I would have said, yeah, but it won't be a real circle, because predicting it was going to be a circle would have been a precise prediction, and when it had come out like that, I would have felt upset. But so it's kind of interesting that it really is a circle. And it's not, right, it's an image rotation, so there is a little bit of noise on it as well, because as you rotate the image, you have to do some bilinear interpolation on where the pixels are, so the pixels don't just jump from one square to another. It's quite a nonlinear operation. So we're looking at the first 2 components of that data. So this is a plane in a 3,640 dimensional space. It actually is saying that this space is 2-dimensional or linear and trying to find the direction of largest variance is how typically PCA is introduced, projecting onto that. And we see that there's some particular features. There's some little twists at the side of the data. But other than that, it's broadly right on the same place. Now what I want to do, let's ignore that slide, is actually look at these squared interpoint distances for this data. So remember I said my data was y, so this is the squared Euclidean distance between all data points yi and yj, right? And we're going to compute those, and I prefer to think of them in vector forms rather than by writing an L2 norm, so I'll tend to write in vector and matrix forms. And we're going to, and that leads to a matrix, right? If we get all those squared elements together, that leads to our big matrix D. And this is what it looks like. Isn't it pretty? What is this feature? Anyone? There's a squared feature on there. What's that feature? You're seeing the degree of rotation is a clue on the side. It's a feature that appears at 90, 180, 360 degrees. What's the feature? Come on. What are we doing to the image? Rotating it? What's special about a 90-degree rotation?
Pixels are matching exactly.
Pixels are matching exactly, yeah. I really like that picture because it actually shows you a feature in the data that you could a little bit see. Because what you actually see, thanks you, is the pixels match exactly, but just before they match exactly, they go a bit crazy. Because the bilinear interpolation is worse just as you're getting to that degree. And I didn't know that, but you can see it in these little visualizations. Here, 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 and here. So actually what you're seeing is the noise getting worse and then collapsing down to exact. So there's a heteroscedasticity in the noise. I mean, that's not... It's interesting that you can see it. It's a very fine feature, though, isn't it? Now, I want you to bear that in mind, because what I want you to do is think about how can we... What we want is a reduced dimensional representation of this data set. And one way of thinking of what we want, distances are important, interpoint distances are important. Look at these nice features we can see. I want to do such a thing that preserves all these distances. So reduced dimensionality representation that preserves the distance between any 2 points. And that's going to be my starting point. So, find a configuration of points such that each distance in the latent space, closely matches the corresponding distance in the data space. So delta is a distance in the latent space, square distance. So this is a very odd objective function. I'm not going to derive the algorithm. But this is an objective function that appears in Mardia, Kent, and Bibby. If you're into multivariate analysis, read that book. It's 1979. I've spoken to John Kent quite a lot, and he tells me they keep getting asked to update it, and they just haven't got around to it. If it's Kanti Mardia, John Kent, I don't know Bibby. But it's a really good book on all the different approaches, statistical text on multivariate analysis. And it has this thing in there which I don't think people notice very much, which sort of says that if you want to, I mean, when I'm sort of thinking about matching distances, I want to know, well, I need an objective function. And it mentions this objective function, which is a slightly odd objective function. This objective function is take that matrix of square distances and take the L1 norm between all the distances. These are the distances you're computing in, square distances, sorry, in data space, and these are the ones in latent space. Minimize the L1 norm between those two. Now, it's a funny, I mean, there's nothing necessarily wrong with it, but you would think someone would have to justify that to do it. But the interesting thing about it is, if you want to minimize that, the answer is, if you're going to select for x, if you're going to choose x by just choosing columns of y to represent your data. So we're going to do a very simple dimensionality reduction. We're not going to do anything, it's not even, it is linear, but it's not even a general linear dimensionality reduction. We're just going to choose pixels from that digit thing that we just retained. So we're going to choose specific pixels that we retain, specific features. And we're going to choose them such as to minimize this error. And if you do that, it just tells you something very simple and obvious in retrospect. You can do the derivation. It says, choose the columns of y that have the largest variance. Look at where the variance is largest and choose those that have the largest variance. So if your data was isotropic, as someone mentioned before, you would be in a bit of trouble. So you just measure the variance independently of every dimension and choose the ones with largest variance. Oh, duh. Well, obvious, because the ones with largest variance are the ones which are contributing most of the distance. You know, it takes a lot of work to prove that. But oddly, it's this objective. It's not necessarily clear that that objective will lead to it. And it's the only place where I've sort of seen that objective being used to demonstrate that. So this is a reconstruction of that data set. And the error measure is that measure we've seen before, but it's a mean absolute error measure of the square distance reconstruction of choosing just 2 dimensions. So this is a 2-dimensional representation. Now, of course, these are discrete pixels, so we're seeing a lot of structure in the distances here because it's on and off these pixels. But so that doesn't look quite enough to get that structure we're really seeing in the data, does it? Certainly we're missing those 9 features at 90 degrees, 180, and there's a feature at 270, but I think that's just coincidence. 10 dimensions, so 10 pixels being used to represent the data. 100 dimensions. Actually, now at 100 dimensions, you're sort of hallucinating a little bit some of those features, right? So 90, 80, 270, but there's something also here, so you're not quite seeing those features clearly. So if you're just measuring the distance by by taking the highest variance 100 first dimensions and using that to reconstruct the distance, 1,000 dimensions. So it's a 3,648 dimensional data set. We've had to use 1,000 dimensions, and now we really see the structure. I don't think that's too different, certainly by eye. And look, the mean absolute error is 0.109. So that seems good, but interesting point. If we rotate a data set, what we're doing here, this is the first point, is what we're actually doing is we're taking away a dimension. And so this has got interpoint, we're not rotating here, we're projecting onto this axis. There are interpoint distances here that we're looking to preserve, and what this algorithm is saying is instead of choosing the low variance dimension here, choose the high variance dimension. And we do that, and we project onto that. That's preserving the distances as best as possible. But there's a much better thing to do. If instead of doing that directly, we rotate the data set first, such that the highest variance dimension is aligned with the direction we're going to keep, then we preserve more of the interpoint distances when we take the projection. So because interpoint distances, we can take any data set, that's preserved, that's going straight to the axis, right? So actually it squashes some of the interpoint distances lost. But by rotating our data set first, we can preserve all the interpoint distances. And we retain more of that structure. What is that algorithm called? PCA. Principal Component Analysis. I made a big fuss last time. PCA is not an algorithm. And this time I'm introducing PCA as an algorithm. This is how everyone sees PCA introduced. Well, they don't get it introduced like that. They say introduced, you want the direction of lateral variance, blah, 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 blah. Why am I doing it this way? This is not how PCA was invented. PCA was invented the way I talked about it last time. This is the wrong way to think of PCA, but it's the way everyone thinks of it. So that's fine. It's good when everyone's wrong. This is an interesting algorithm, though, and it's actually suggested by Pearson in 1901, I think, whereas PCA was suggested by Hotelling in 1936. And they both suggested 2 different things. One was suggesting a probabilistic latent variable model, which is the sort of thing I'm more comfortable with, and the other one was actually suggesting if you're trying to regress from x to y, you get an asymmetric regression if you regress y to x. So Pearson was looking for a way of finding a symmetric way of regressing between the two. And then he said, well, actually, it turns out to be the direction of largest variance. And everyone therefore says Pearson invented PCA. And that is utter rubbish, because Pearson wasn't inventing PCA. He was looking for different directions. He didn't name it as such. And what he was trying to do was totally different to what Hotelling was trying to do. But when you generalize Hotelling's, so in a linear case, they lead to the same algorithm. If you non-linearize these 2 ideas, they lead to totally different things. Utterly different things. And that's really, really important. PCA is some weird algorithm. PCA is some weird model. PCA is like the algorithm associated with a bunch of different models. And it's critical to sort of understand it that way. And this is one. We haven't even described a model. So what we're going to do as a quest now is take that and move that forward into a whole area, a whole domain that wasn't even introduced as being a variant of PCA. It was introduced as being these spectral algorithms, and sort of review them that way. They're not that popular, actually, nowadays. Everyone's into deep learning. But don't worry, they'll come back, because everyone was into deep learning 20 years ago. And, these things just go around in cycles. What we want to do is find the rotation that will minimize the residual area, and then we discard the minimum variance directions. And that rotation is the diagonalization of the covariance matrix, its principal component analysis. I don't want to go too much through the algorithm. That's how many dimensions is that? I've lost the dimensions. Where does it say the dimensions? That's 2 dimensions. I remember the dimensions. Yes, it says 2 here. Sorry, yes. That is the 2-dimensional reconstruction of that data set with 2 dimensions. 2 dimensions. That's the thing I showed you at the beginning. Look at that. Okay, the structure's wrong. This structure's too wide. But already, the mean absolute error is really small. Like way smaller than 1,000 dimensions from before. It's a brilliant algorithm. This is 10 dimensions. This is 100 dimensions. This is 360 dimensions. What's special about 360 dimensions? 1 per digit. That's actually the exact reconstruction. Mean absolute error is 0 because 360 dimensions is the maximum dimensionality of this data set because there were only 360 data points. So you can't actually, the structure of, it's determined, the structure, the number of eigenvalues that are in the problem is a rank. The matrix we are creating to do this analysis, in effect, as we'll see in a moment, is rank 360. So we can't go to 1,000. We can't even look at 1,000-dimensional space. But that, way better if we're interested in this distance structure. And the interesting thing about this is if you look at things like Mardia, Kent, and Bibby, they'll talk a lot about these sort of things. Classical multidimensional scaling methods, similarity measures, moving between distance and similarity, stuff that is widely ignored in machine learning. And I think it must be very irritating to people in other related fields when we're so ignorant of this stuff. And it's elegant and simple, so that's kind of why I like to talk about it. So we need to find directions in the data which have maximal variance, and that's exactly what principal component analysis does. So principal component analysis is the algorithm that will do this for us. It's also the algorithm that underpins probabilistic PCA from last time, but I non-linearized probabilistic PCA in a particular way last time, and we're going to non-linearize PCA in a totally different way this time. So it's not even obvious, probably, at this point, why people know that PCA is linear, but the reason why I haven't introduced it with an affine transformation. The reason why it's a linear transformation is because it's a rotation followed by a removal of dimensions. I mean, you can either include the scaling in there or not. If you want to actually have your principal components reduced such that they're variance 1 in the latent space, then you scale as well. If you're trying to reconstruct distances, you don't do that, right? That scaling would just damage the... so that it's a sort of trivial whether you scale those latent dimensions or not. Okay. So actually, this is not known as principal component analysis. This is known as principal coordinate analysis. Or when I first sort of came across this thing, I talked about it as dual probabilistic PCA because I came at it from that direction. You typically, when you do PCA, you work on the sample covariance matrix. But one of the sort of known things about PCA is you can either work on that sample covariance or something that takes the form of the similarity matrix. So people looked at this in statistics. What you would normally do for PCA is take the sample covariance and you do the eigendecomposition of that sample covariance in order to get the rotation and the scaling, and then you map your data doing that. But sometimes working with that sample covariance is impossible. And this is where areas like classical scaling come in, classical multidimensional scaling. So, for example, you're given distances between data points, but not absolute locations. So your data set is not in the form of, here's some y locations, and then you can go and compute the distances. You don't actually get to see the distances. You just get to see, so you don't get to see y, you just get to see d squared. Someone's pre-computed d squared. This comes up quite a lot. For example, we'll do an example in a moment where it's clear that it's there, but another example, which I think I mentioned in a future slide, is in psychology, they don't work with distances or covariances directly, but they work with, say, similarity measures. So you might do a psychology experiment. I ask all of you to give me similarities between different colors or something like that. And then you score each color for a similarity. I then assume that matrix is symmetric. I don't see your absolute representation of the color. I just see what you're thinking about two colors relativity. So classical scaling methods are used often in psychology to take data like that and represent it in a way that we can process. So principal coordinate analysis actually is the sort of object people typically use for this. It's the model that we've really been describing, because it operates, instead of operating on the sample covariance, so I should have made it clear when I had it up, This is the sample covariance matrix in matrix form. It's the sum of y minus the mean of each y times the same thing transposed. But it's in matrix form here. Y hat is a centered matrix Y. So y hat is the Y with the mean removed. It's just convenient to not carry the mean around. So that's S, in my notation, that's the sample covariance. I like that notation because it makes the relationship a lot clearer between the thing that we're actually going to look at here now, which is this, the inner product matrix. It could be a centered inner product matrix. Often people don't center their inner product matrices, but why not? You could center it. So this is something that comes up a lot in machine learning because it leads to sort of the ability to kernelize, and indeed we will do that in a bit. So the interesting point is that you can either do, to solve PCA, you can either do the eigenvalue problem on Y transpose Y, or you can do it on YY transpose. One of those eigenvalue problems solves for the rotation you require, and the other one solves directly and immediately for the location of the rotated points. So that was in my slides from last time. But that's a sort of known trick. So the point is, for example, on this digit data set, which is 3,648 dimensional, if you do the eigenvalue problem on the 3,648 dimensions, you're basically got a cubic in 3648. If you do it directly on this, you're cubic in 360. Actually, you shouldn't do it either way. You can just do QR decomposition on Y or single value decomposition, but theoretically. So typically, you're more interested in this eigenvalue problem if n is less than p. And n is less than p is where we're at. There's a whole thing about n being less than p being a problem. It is absolutely not a problem. I mean, there's a massive fuss about it. It is a problem for classically defined models that assume independence across data points. What we're going to see by the end is if you assume independence across data features, then you can handle high-dimensional data very easily. And it turns out a lot of what people are doing is exactly that. So, that YY transpose is actually something like a similarity measure. It's like a covariance matrix. It's not a distance matrix. So the first thing you need to do in multidimensional scaling is, if you're given distances, can we compute, can you go from the distance matrix you're given to this object YY transpose that we can do an eigenvalue problem on? And that's the sort of, again, I don't know, these sort of things were sort of reinvented in machine learning, but quite widely known outside. So now we have to do a matrix form of the squared distance. Now the squared distance matrix is of this form. Diagonal of y transpose. That's me trying a lot of matrix work to extract elements that are yi squareds, right? And then multiplied by 1 transpose. So you've got a row vector of yi squareds being dropped down like that. And then conversely, you've got a column way. This would be like the ugly MATLAB way of creating a distance matrix without doing really fast, without doing a loop. And then here, in the middle, you're taking off. So you've got the sort of yi squared plus yj squared minus 2yi yj. This is just the matrix representation. Why have I got that matrix representation? This is a centering matrix. It's a cool matrix that you can use to take the mean of something. It's also how people tend to do it in MATLAB. Don't do it in MATLAB like that. But do it mathematically. It's a lovely mathematical matrix because it's a matrix that subtracts the mean off a matrix of data. So it's a really nice thing for that. The reason it does that is because it's of this form. And if you sort of multiply it by y, you get I times y minus 1 over n times y times 1, which is the mean. So those bits give you the mean, and then this bit does that nasty MATLAB trick of mapping the mean up so you can subtract it off the original data. So this is the centering matrix. If you take y and you multiply y by h, you've just got y hat, y with its mean removed. You don't really, you don't do that. You're not supposed to do that because you want to. Don't start implementing it out in code like that. It's a mathematical convenience. The interesting thing about that is you can see very quickly that this is true because h1, so this is the vector of 1s, I should say. It's got a null space in 1 because h times 1 gives you 1 transpose 1, which is n, 1 over n. So times I times 1 here is the matrix of 1s. So you get 1 minus 1, 0. So the centering matrix has a null space in 1. So what happens when I center the distance matrix? What does it immediately do? Kills the first and last term. Yeah. So if I center y here, if I center on one side and center on the other side, that disappears because of this, and that disappears because of this, because I've got one coming in from each side. So a center distance matrix is just minus 2 times the inner product matrix. Who knew that before, by the way? Just a show of hands. 1. Excellent. Isn't it shocking? Isn't that utterly shocking? This is why I'm not teaching about deep learning, because you don't deserve to know about deep learning until you know that. There should be a test every time someone wants to speak about deep learning. I have to check that they know this. It's really, and it's in Nadia Kent and Bibi, and it actually is related. I'm going to show you, I think it's related to that people do know about a bit more in machine learning. So this implies that if you're ever given a distance matrix, you want to turn it into an inner product matrix, then you just do the centering operation. And you can now play with that inner product matrix as if you were given the inner product matrix directly. Of course, you have to multiply it by minus half. It's cool, that, isn't it? Okay. So, but this Y, transpose Y, is the data covariance, right? We know that. Everyone talks about it as the covariance. But this Y transpose also has an interpretation as a covariance matrix. It's kind of an estimated correlation across the data points. If people are familiar with Gaussian processes, it's an n by n. So this object here is, if we're trying to estimate, we'd have to put a 1 over p in front of it, actually, strictly speaking. If we're trying to estimate the covariance between data dimensions, it's that one. If we're trying to estimate the correlation between data points, that's how we estimate it. So it's expressing correlation and anti-correlation between our observed data points. So now let's think, what if we want a probabilistic model to sample from to generate those things we were seeing before, the interpoint distances? This is the obvious object. It's the interpoint matrix between data points. It's very easy. If I know that that's the covariance of my data, it's very easy for me now to say, if I'm going to estimate my covariance of my data with that, what my expected distance is between each of the data points. Are we in time? All right. We're going to put what? Yeah. He understood. Yeah, okay. So let's have a look at what that implies. So if it's a covariance across data points, if we sample Z from any Gaussian, doesn't matter what the Gaussian is, it could be whether this is p-dimensional or n-dimensional, doesn't matter. And then we sort of take 2 elements, 2 one-dimensional elements from that thing. So these are not vectors, they're just one-dimensional elements. And we say, what will we expect the distance between any 2 samples to be, between those 2 points? This is the answer. The expectation of that. Now you can see why I always use squared distances, because it's easy to write down these things. It's this. Expectation of Zi squared, Z squared j, minus 2 Zi Zj, which, if it's zero mean, is just the covariance of the variance of Z plus the variance of Zj, the variance of Zi plus the variance of Zj, minus the cross covariance between Zi and Zj. That is kind of thought of in machine learning as, sometimes it's called the distance in feature space, the distance in kernel space. I don't think of it like that way, because people think of it that way because they talk about infinite dimensional feature spaces. And I really struggle to think in infinite dimensions. It's just a problem I apparently personally have. Whereas this is really interpretable. It's just telling me the mean expected value of the squared distance between any 2 points sampled from a Gaussian. And of course, why am I introducing it? Well, if that covariance of that Gaussian was YY transpose, it would be that. It's just the Euclidean distance we had before. So somehow, when we look at distances in this way, we sort of see this duality between the Gaussian density, an attempt to sort of convert distances to similarities, algorithms that measure square distances between 2 different, in a latent space and in a data space. And the interesting thing about this is, if we're going to build, so another way of sort of saying of what we did was, so this is a bizarre explanation for PCA, that we have a model for our data of this form. We then fit, by maximum likelihood, the optimal form for k. And in that case, k will be 1 over p y hat transpose, taking the mean out, centering everything. If we had the mean in there, the mean would just appear in lots of ugly places and make it less clear what's going on. And now we've got a Gaussian model. And our next step is to say, well, I want to take this Gaussian model and I want to peer into this Gaussian model and try and understand how I can have a low-dimensional representation of that Gaussian model. And then what we're saying is, in order to do that, I'm going to do the eigenvalue decomposition on the covariance matrix and sort of look at the points projected in that way. So it's a very long-winded way around of just getting PCA again. Now, the really interesting thing that happened in machine learning, 15 years ago, was that people started to non-linearize this. But I don't know, these non-linearizations really confused me. They didn't introduce any of it in this way, and I was always I wanted to teach that. Probably I wouldn't bother teaching it now, but apart from today. But I wanted to sort of get across how everything's stitched in together. So it took a while of thinking to start describing it this way, because this is going to be the starting point for non-linearization. So after the break, what we'll first of all do is the sort of thing that naturally people do a lot with their data, kernel PCA. It's a classical sort of approach to dealing with data. And we'll see what it says, what it tries to do to non-linearize this algorithm and get nonlinear dimensionality reduction. Then, probably with increasing speed, we'll cover various other approaches, such as locally linear embedding, isomap, and Laplacian eigenmaps. Probably in the reverse order to what I said, I'm not sure. Each of which can just be seen as a way of specifying this covariance matrix in a constrained form. Placing constraints on what you think of as that covariance matrix. Then right at the end, we're going to pull back to my favorite algorithm, which is the Gaussian process latent variable model, which can also be seen as this form, but very different treatment of k. So like every model we're talking about turns out to be some form of specified constraint on the form of k. My GPLVM it's a covariance function. And the elements of that function are actually the latent variables and you optimize with respect to them. The other forms are actually more of the form that the inverse of this matrix is sparse. That what you're actually saying is, in your data, the inverse of that matrix is sparse. And what that turns out to mean is that you don't care about reconstructing all distances. It turns out to mean something very, very obvious. It says that don't try and reconstruct all distances. That just be done. Just construct the distances of you and your neighbors. And if you impose that sparse structure on this inverse covariance, you get pretty much all the spectral methods that people are using. The nice thing about that, though, is you have a much better interpretation. So we're reversing things. So we're going from model to algorithm, which is the way I like to do it. And I'm not saying you all have to do it that way. The thing I love about machine learning is the diversity of approaches. And when someone does something, you think, well, how the hell did you come out with that? Just by trying to understand it, you can learn more. And for me, this whole process is that. I think I learned more. How about how these methods unify? So, but we've basically we've now got a model in place. I mean, it's not actually the model, it's not clear why that's a dimensionality reduction model. But we'll come back then in, at 3 o'clock and continue then. What happened? Okay, so this transformation is actually quite widely known, and this is what I mean, I really have to say, it's funny when you go to machine learning conferences now and everyone talks about their backpropagation algorithm, because it's kind of feels a little bit like it felt in 1996, 1997. And even then, we weren't paying close enough attention to some related areas. So this transformation is actually the kernelization of a distance, it's sometimes known as. But it's in Madhya, Kent, and Bibby, and it's known by them as the standard transformation, 1979. And it's sort of being suggested as a way of moving between the similarity measure and the squared distance measure. And it's suggested for things like psychology, where you get a distance matrix, a similarity matrix that you want to map to distances and back, and all these sort of things. It's quite interesting. So this is a little example of this with classical multidimensional scaling. I love this example because it sort of works so nicely. I did this a while ago. It's It's a classical example from Mardia, Kent and Bibby. They do it for Britain, because it's 1979. Britain was still an important country. But in 2015, it feels more appropriate to do it across Europe. So road distances across Europe. So we can get now a square distance matrix of all the cities across Europe. So we can represent the cities' locations by looking at the square distance between them. And we enter this in a matrix. We convert to a similarity using what I call the covariance interpretation, but you can think of it as the standard transformation. I call it the covariance interpretation because to me that's got a real physical meaning. You're saying something about these dimensions being sampled from a Gaussian covariance, which I'm very comfortable with because I feel that's a Gaussian process. And then you perform the eigendecomposition because that gives you a low-dimensional space where those low-dimensional distances, but notice it's a separate step. It's like you fitted this sort of Gaussian type thing, or you develop this step, and then you do the eigendecomposition. So the data is available on there. This is the transformation. This is what it looks like. These are we'll see the cities in a moment. These are all the squared distances between the cities, and then this is centering and then dividing by, then taking minus half of that matrix. That gives us the similarity matrix between the cities. So you can sort of see the places that were close together have become similar. So low distance becomes high similarity, as you'd expect. So that's the distance matrix and the similarity matrix. And this is what you get in terms of the bits that are in the C. You can guess which ones are the real data and which ones are the fake. So this is just doing that, looking at the first two components. Sorry about the green. It's a bit bright. This is using the mmap toolbox in MATLAB to visualize this. The way of getting these crosses as close as possible to the truth is called the Procrustes rotation. Procrustes, so you solve when you get these systems, you solve them up to a rotation. So I've resolved the rotation by trying to match my projections as close as possible to the underlying data points. So they don't project exactly to their location. So Edinburgh's moved a lot closer to London, as has Dublin, which I'm sure doesn't go down. There's a lot of political bad stuff going on. I mean, it's I think it's cool. You're sort of extracting the structure of Europe just by road distances. Now, one thing you have to be a bit careful about when you do that is that these distances aren't Euclidean. Distances across roads aren't Euclidean. So if you look at the eigenvalue spectrum of this distance matrix, or the similarity matrix you obtain, so one thing that is sort of known is that this similarity matrix should be positive definite if the distances are Euclidean. But we've not constructed these distances in a Euclidean manner. So in the world of kernel methods, this leads to a non-positive definite kernel. The similarity measure we're computing, which is why often people will say similarity measure and not covariance, because it's not a valid covariance, because it's got negative eigenvalues. Because the covariance is about distances in Euclidean space, because the Gaussian is across Euclidean spaces. So when you look at what the implied covariance is, you get negative eigenvalues. And so you have to be a bit careful. You can't feed these things directly into kernel methods. You have to know what you're doing. But this was widely known in classical multidimensional scaling for quite a long time. And what we've just shown you is classical multidimensional scaling. It doesn't worry them too much. They just proceed. They just take their largest two eigenvalues. Sometimes there can be a lot of meaning in these. But it's still these ones that are showing you where the dominant distance is represented. So if we look at the reconstruction, it's pretty good. That's the original d squared, I think, and then this is the delta squared reconstruction with 2 dimensions. I haven't shown the mean absolute error, but there's a lot. Most of the features you see are sort of in there, aren't they? It's a nice reconstruction with 2 dimensions. Okay, but that's linear. So that's very much a linear model. So you can use the similarity of the distance measure of your choice. If you read, there's a very I found it a very disappointing book, Cox and Cox, Multidimensional Scaling. Why do I find it disappointing? I felt there's far more insight. I loved Mardia, Kent and Bibby on this area. It's really informative. It's quite technical. There's a lot of stuff in it, but it's just such a wealth of material just in that chapter. So I got Cox and Cox. I thought, Cox and Cox is the classic text everyone references on multidimensional scaling. It's kind of, maybe it's useful for statisticians. It's just a list of different ways of making distances out of different data types in different chapters. with not much insight. So for me, it didn't do a lot. But my dear Kent Bibby does a lot. That's a great reference for this. But the key challenge, as I said, is how do we go non-linear? So this is one idea is to use the linear algorithm, this classical multidimensional scaling thing, which is just sort of rotating these spaces around and projecting into low dimensional, but make the distances we compute from non-linearly related to the data. So if we're given y, if we get the ability to choose how to compute the distances, it won't necessarily, in nonlinear multidimensional scaling, and I'm not going to talk about this, in multidimensional scaling algorithms, very often you will do a transformation directly on the distance matrix. And then you do, algorithms haven't done that transformation. I'm not going to talk about that. That's one way of making things nonlinear. That's not what I'm going to talk about. What we're going to do is assume we've got access to y. So we know now that if you've got access to y, you can do PCA directly and recover this. But let's assume we've got access to y. Then we do a nonlinear transformation of y, and then we compute the distances in that dimension. So here's a way of doing that. So this is a neural network. No, it's a basis function model, which is a neural network. And what we're going to do is we're going to transform by mapping from our y data to some new space. So I'm calling f. Damn it, I thought I'd fixed that. Oh. And then the distances we're going to work with are the square distances between two f's. But what should we choose for our parameters? That's tricky, isn't it? How are we going to choose our parameters to do this operation? Any suggestions? Let's not choose parameters. Let's assume they're sampled from a Gaussian distribution. And to show you that idea, so I'm going to consider basis functions which are Gaussian sort of bases. So these are the nonlinear functions that I'm mapping to. And I'm going to sort of build a design matrix out of that. Well, let's just go on to the sort of plot that... Oh, I hope it's still there. Yeah. Let's visualize what I'm saying first. So I expected these slides to come up next. So this is my original data y, but I'm not going to compute the distance in y, which would be that, the square of that. I'm going to map it first through f of y, through a function, and have the distance there. But which function should I be choosing? Well, here's a function that's created by adding a couple of basis functions together and mapping through. But rather than doing that, I'm going to look at the whole class of functions. So let's just get where I want to be. So, yeah, sorry, I do need to go through this a bit more slowly. Here we go. Okay, it doesn't matter what our basis function form is for this next bit. But the way we tend to take basis functions and deal with them in practice if we're doing generalized linear models is we build a design matrix of the basis functions. So I'm calling that phi. So phi is a design matrix of all these little basis functions. The basis functions are being summed together. So it's a linear combination of some nonlinear basis function, which I'm saying, let's assume it's Gaussian, to give us this fi. Measuring the distances, that should be fi minus fj squared. And what I'm going to do is I'm going to think about that, first of all, in the vector form. So that means that instead of the sum, I'm just showing w transpose phi I, where that's a vector of all the basis functions to give me my output. Because this means I can now write my squared distance in this form. Yeah? That's just fi minus fj. So nothing's changed here apart from notationally this is a little bit more convenient. If I multiply out that, I can actually write it in this form. Now, if I choose to sample these variables from a Gaussian density, so I don't want to choose these w's. What should the w's be? Who gave me the right to choose w's? I don't have a right to choose w's. I've got no way of fitting them. Let me just say I'm going to make w a draw from a probability distribution. In fact, it doesn't even matter whether it's as long as it's a zero mean probability distribution. It doesn't have to be Gaussian even. If the covariance of that distribution is I, then what we find is that the distance between these 2 points on average will be this. So it doesn't even have to be Gaussian. It just has to be a probability distribution. If we look at the expected square distance, so what we're saying here now is I'm going to get the expected square distance by mapping randomly into some space. You can think of it as a one-dimensional space. Don't even think, oh, this is going to an infinite dimensional space. We're just mapping to a one-dimensional space, and we're only asking the question, what is the expected square distance between any 2 points in that space? Does that make sense? Clearly it non-linearizes things. Seems a really cool idea. Okay? So let's look at one sort of problem with this idea. So here's our basis functions. We're going to compose these class of functions by summing these three bases with, let's assume, Gaussian distributed weights. It doesn't have to be Gaussian, as I said, but let's just assume so. So here's a couple of points and how their new distances will emerge from those couple of points. So they're close together in the original space, they'll be close together in the other space. Same with those 2 points here. Each of these, they work really nicely. So we're actually just going to get some sort of nonlinear relationship between those 2 points. So that seems to be good. What happens, though, if our basis functions are here and we start seeing points at the outside here? So these 2 points at -3 and 3 are a long way away from each other. But because the basis functions are at 0, they map down to be very close. So this can happen when you do this sort of thing. When you do these types of mappings, you can take things that are far apart and map to be close. So this is actually quite a bad idea to do this. So distances are small despite the data being far apart. And that's a side effect of bad basis function placement. So this, if you were to do this algorithm, which I never have done, you would really have to watch for that. But the beautiful thing is, there's an elegant solution for this, that you don't have to choose your basis function placement. You can show that kernel methods, the Gaussian process covariance function methods, allow you to place those basis functions across the entirety of the real line. So rather than having a parametric form, and I'm not going to go through the maths, you can start sort of saying, well, I'm going to have a sum from k equals 1 to m of a load of basis functions, where the location of each basis function is of this form here, and then I'm going to take that sum to infinity, so that the basis functions are across the entire real line. And you can do this for quite a large class of basis functions, and what you actually get is a covariance function, a kernel function. You get that if you do that inner product that we had for the basis functions before, you have to solve it with an integral because it becomes an infinite thing. You end up with a kernel matrix. So going back to, I mean, this sort of should now be, for people who are used to kernel methods, this sort of becomes obvious. This is a feature mapping in kernel parlance. And the square distance you're looking at is simply the kernel-based feature mapping. So if I take this, what I've been suggesting is that the dimensionality of these things is fixed at n. If I take that dimensionality to infinity, it's still the same thing. Now, people talk about that again, as I said, as the distance in feature space. If you're a Gaussian process person, that's much more naturally thought of. And I never see anyone else talking about it like this. Maybe they do, but I haven't seen them. I think it's much more naturally thought as this expectation between 2 points. Don't think about infinite data spaces, just thinking Gaussian processes. And that expectation is precisely what we're seeing here, right? Physically, it's very easy to think about. It's the expected distance between any 2 points. Now, what happens for that then? So anyone want to tell me, in a Gaussian process case, what would happen in this case where the 2 points are very far apart compared to the length scale of the basis function? 0? Distance in the similarity would, but what would the distance do? What would happen to this distance? You're 0 in terms of the covariance, yeah. That's absolutely right. Here the distance is going to 0, which would mean that the similarity would be large. In the covariance function for the GP, the similarity, you're right, would go to 0, but what would happen to the distance? Remember that formula, KII. This is the formula of the expected distance. KII plus KJJ minus 2KIJ. So what would the square distance be? If the similarity between those 2 points is 0, and let's say that the variance is 1, KII and KJJ are 1, so it's a covariance function that's isotropic.
2.
Yeah, 2. Yeah, square distance is 2. So this is really an odd thing now. And actually, it explains a lot about kernel PCA when you realize this. Every distance of anything that's dissimilar must be embedded square root of 2 apart. What does that mean, by the way? What space must they be embedded in? How can you get things to be all embedded a long way apart from each other with the same value? High dimensional space. Kernel PCA increases dimensionality. You never see that written about. It's kind of obvious in retrospect. In fact, it is written about in Maximum Variance Unfolding, a nice paper by Killian Weinberger and Lawrence Saul, where they are actually explicitly aiming to address this problem. And they don't constructively talk about it in this way. But it's all retrospectively obvious now, isn't it? The kernel PCA is trying to increase dimensionality. In fact, kernel PCA at its limit, as you reduce that dimensionality, the length scale of the kernel you're using in PCA, everything becomes dissimilar, and basically it just embeds everything square root 2 apart. The way it does that is it puts everything one away along every axis. Now, that's not a bad thing if you want to do feature extraction, feature expansion. If you've got a data set and you want to say, I want to expand this up, blow this up, and look at some interesting space, it's a really interesting space to look at. And everywhere you see kernel PCA being used, that's what they're doing. It's not a dimensionality reduction algorithm. Which you sort of would expect it to be because it's kernelized PCA, right? Because the end result of this is you put a kernel matrix and do the eigenvalue decomposition on the centered kernel matrix. That's what this comes out as. In order to look at these expected square distances are now going to be our distance matrix that we're going to use in our algorithm. They're nonlinear, so it's a nonlinear algorithm. And what we know the right answer to do is take the square distance matrix and center it, and then do the eigenvalue problem on, and that turns out to be just do the eigenvalue problem on K. Because what you're reversing, all you're doing is reversing the, that's your square distance matrix. You do the centering, which knocks out that bit and that bit, and then you're left with this bit here, Kij, that has to be centered. The centered kernel matrix, which you then multiply by -half to get the similarity matrix. So you just end up doing the eigenvalue problem on the centered kernel matrix, which is fine. But it's not a dimensionality reduction algorithm. It's a dimensionality expansion algorithm. So it's questions about that before we move on to the wider class of spectral methods. How you get something that do dimensionality reduction? Yeah, so of course I think that's a guessing process. You can think about its features, and that's not how they introduced it. And I think you can't find it written about in that way. So this is now, look, this is what we were talking about, is now far apart distances on average will be quite a long way apart. Sometimes they're close, just by coincidence, but this is a sample from a Gaussian process, in effect. This is the new distances you're trying to represent, the average square distance, not the average square root distance, I should say. I just find it hard to plot the square distance on the plot. Okay, so this is the sort of similarity matrix for what I call the exponentiated quadratic kernel, the very widely used covariance function, the RBF kernel. And this is the implied distance matrix. So what is the dominant thing? You can hardly even see it. What is the dominant thing in this implied distance matrix? Bear in mind, it's trying to approximate the implied distance matrix by looking at an L1 norm between your latent space representation and all elements in this distance matrix. It's trying to approximate this bit. That's where the structure in the data is. So it's kind of hard to see. Is there maybe I can turn off at the front. It's good on this screen. 3 is audio-visual. Yeah, sorry, it still doesn't come out that well. The length scale is small enough that basically there's just a band down there where there's some structure, and every other element in the square distance matrix, or the distance matrix is square root of 2, the square distance matrix is 2. Can't remember what that is. Apply distances for kernel. Looks cool though, doesn't it? I think that is implied latent distances. Right, so this is if I do kernel PCA, this is my reconstruction of that, I believe. So implied latent distances for kernel using only Q equals 8 dimensions for latent space. So we're taking kernel PCA using 8 latent dimensions, and then we're looking at the distance in those latent dimensions. So it's actually trying to reconstruct all these off-diagonal elements as well. But it's going to struggle to do that. It's going to struggle to do that until it gets very, very high dimensional. Right? You have to have all, you go back to having all the dimensions in before it can reconstruct that matrix. So I guess it's what the interesting question, which I'm not really telling you much about, is what those dominant directions are. And they're to do with eigenfunctions of the kernel. So they are interesting nevertheless. But the point is that it's not a dimensionality reduction. So this is sort of so this is the rotated sixes. And this is 3 dimensions of the rotated sixes. So this is all being the rotated sixes, but this is 3 dimensions. I'm just wiggling it about to try and give you an impression of the 3D nature. I mean, the PCA thing's way simpler, isn't it? PCA showed us that it was 2-dimensional, didn't it? The data was 2-dimensional. We can't even reconstruct it in those distance sense, which might not be the best thing to do with 8 dimensions now, because we've turned all the information in the data into many, many, many dimensions. Okay. So what's the solution to that? Well, the solution to that is to do something a little bit funny. There's a really odd aspect about this, which will emerge later. Normally, the way you get something to be nonlinear is by introducing more parameters. Whereas in this case, you get things to be nonlinear by having less parameters, less constraints. Certainly when you see it as a spectral method. So nonlinear algorithms actually turn out to have less parameters. And the reason is, the way you get something to be nonlinear dimensionality reduction is you stop trying to reconstruct all the distances. It's clearly a very bad idea. Why reconstruct? What we're doing in this case is we're saying reconstruct the distances of things that are very far apart. But it naturally makes sense to say, if I'm going to do dimensionality reduction, I think something nonlinear has happened. If I go from a low-dimensional space to a high-dimensional space, things that are close together will map to close together. If things are far apart in this data here, it sort of doesn't really tell me much about where they were in the latent space. So why am I trying to worry about all of these things? Why don't I just look at things? What I would really like to do is know who was close to each other in the latent space. Right? Ideally, and I don't think this comes through in the papers, but certainly I feel this, if I knew the latent structure, like who in this latent space was close to each other, then I could try and work on making the distances I observe in data space match those in the latent space only. And that would allow me to think of it as a nonlinear sort of mapping. See if that idea comes through as we go through these classes of algorithms. That's basically what all the spectral methods try and do. So the spectral dimensionality approach reduction is convert data to a matrix of dimension n by n. Whether that's all these methods are the same, and it takes a while before you have to see all the stuff you've seen to understand how they're related. Visualize data with eigenvectors of matrix, one of these matrices. Sometimes it's the eigenvectors, it's the eigenvalue decomposition of the smallest eigenvectors, smallest eigenvalues. They all vary, but they all turn out to be the same thing. These class of algorithms, including that one we've just seen, are all doing that. So, I mean, it's now 11 years ago or something since people were looking at this, but I think it's amazing how, you don't have to know all these different algorithms once you understand it from this perspective. So this algorithm we've suggested that we've been working on is compute the n by n squared distance matrix, form the centered similarity matrix, HKH, visualize through the Q principal eigenvectors as the latent matrix X. And this is matching the squared distances computed in X to those computed in Y through an L1 error. There's other interpretations of what it's doing, but it's the one I happen to have presented. The main motivation in most work in ML is how to compute this squared distance D, it turns out. That they're all just variations on that. Some of the ways of computing that lead to some big algorithmic advances, including, and I don't really read about PageRank, but the PageRank algorithm turns out to be this as well. So, let's skip that. Let's look at isomap, because it's the easiest to explain. It's a lovely algorithm, it's so sensible, and one of the best. I mean, really, I apply these things a lot as initializations for GPLVMs, and isomap, it's hard to beat. It's basically that road distance thing. Like, your points are now data points in a high-dimensional space. You decide on a neighborhood, and you connect points to each other by roads, and the distance of those roads is the actual distance between those points. So this is like the classical horrible data set everyone uses. It's the dumbest data set to use in this domain because it's actually very low dimensional and high number of data points, and that's not a good domain for these methods. But they weren't dumb when they first used it. It's not dumb to publish papers on it like in 2001. It's dumb to publish papers on it today. Okay. But it's a nice one to sort of visualize, which is why they sort of used it. And what you sort of say is, okay, if these are roads connecting all these data points in this space here, the distance between this point and this point is go along all the roads. Now, this is their visualization. This is their sort of latent dimensionality. And they get that by taking the square. It's very noticeable in their algorithm that they add up the distances between all the points along those roads, and then they tell you to square it, and then they center it, right? It's just classical multi-dimensional scaling on that distance matrix. They don't necessarily present it like that because you don't get papers in science if you just say, I just did classical multi-dimensional scaling on the distance matrix. So I kind of like this, but it's kind of, these problems, all these neighborhood methods have this sort of problem. If this is what I'm sort of saying earlier. This is a GP sample. Lovely. Everything that looks nice is from a GP. This is a GP sample of a two-dimensional space being projected into three-dimensional and then being twisted around to try and help you visualize it. The neighborhood structure in the latent space is this. Okay? And my argument is that's the latent structure you want to achieve because you want to know that that was close to that. But let's look at the distance in data space between, say, 2 points. If we look at the neighborhood in data space. So now I'm going to look at the neighborhood. I think I choose 4 nearest neighbors. And this is like, to me, this is where all these algorithms stand or fall at this stage. The rest is just it's in the details. It changes performance. But what you really want to get is this structure so that you can work out the distance here. So you want to know that that distance is given by that, or whichever is closer of that. But what actually happens if you choose the 4 nearest neighbors for each of these points to get that structure, so the algorithm being, look at your nearest neighbors, that's your road network, is you get this. Oh, sorry, that's the distance. If you choose it in high dimensional space, did I not do 4 nearest neighbors? I've chosen 3 nearest neighbors, something like that. I can't quite tell how many I've chosen. I think 3 at least. Can't see anyone with 4. This is now a problem. Now, can anyone tell me when this is less of a problem? When will, this is a really odd feature that people don't really point out about these network graphs, when will this problem disappear? Under what conditions? Go on, Hugh. No, it goes the other. Well, neighborhoods in 1 dimension are a bit hard, aren't they? What about in 25,000 dimensions? The distances in... What I think happens here is this distortion that you're getting in the data space is not reflective of what's going on in the underlying latent space. Because just as we saw in samples before, if we go back to... So what we're sort of saying is we're looking at distances by summing over. So the sort of thing that goes wrong is coming here, right? So here 2 points are close in the observed space, coincidentally, because even though they're uncorrelated, they just landed together. So this would cause Fi and Fj to become a neighbor in the high-dimensional space. Bear in mind, I'm assuming now I'm actually generating this. I've just inverted the plot, right? Now I'm assuming I'm doing things the other way around. X in, Y out, right? So this is the thing we just visualized is this manifold, and I'm assuming this manifold is in sort of one-dimensional space. These points appear close. These would be neighbors. As you get higher and higher dimensions, if you can assume you've got independent sampling of those dimensions, which we already know is a dodgy assumption, then actually that problem should get less bad. And it does. As you go to higher dimensionality, these neighborhoods get better. Why? Because these distances, if you are assuming, it doesn't matter what you're assuming they're from, if you're assuming they are correlated, they become better estimated because you're sampling across more dimensions to see the distance. So in a very high dimensional space, you don't tend to get these problems so much. So you will see people using these algorithms in very high dimensional spaces. They don't work very well on that Swiss roll, actually. So if you corrupt that Swiss roll with a little bit of noise, they didn't do this for the science paper, everything goes wrong. All their algorithms mess up. Because the graph structure starts coming out like that. And you get shortcuts as well. You sort of get, in the graph, you get shortcuts between different regions of the Swiss roll. Because it's only 3-dimensional, so estimation of those distances is poor. Okay. So this is the stickman data. I like the stickman data because it's just these 3 strides of someone walking, and it totally gets the structure right. It's one of my favorite spectral dimensionality reduction visualizations of this data. It's a really good visualization. What actually happens in the data, I should have played it to you, is at the start he's bent over like this, and then he runs like that, but I subtract the mean off the data, so he doesn't actually do that. What he does is this, like that. So three paces. That's him bent over. 1 pace, 2 pace, 3 paces. The reason it does this is because the guy actually leans. He stands up as he runs. So it's correct that these things do not sit on top of each other because they don't map quite to each other. If you want to think about what this should be, it's probably a 3-dimensional thing. It's more like a cylinder. It's a string going round and round 3 times around the cylinder because one of the dimensions is like his angle of run. It's actually 4 dimensions because that comes off in some odd direction of the starting pose. But this thing here is like a piece of string around a cylinder. It's a great visualization. ISOMAP works really well, and kind of is really simple to conceive and apply, and could be easily taught without all the stuff I just talked about. This is the oil data. So the oil data is not so well visualized by this thing. It's not enough. I don't know what kind of goes wrong. I think it's because it's sort of lower dimensional. That first data set was higher dimensional. 104 dimensions, 55 data points. This is 1,000 data points and 12 dimensional. PCA actually looks quite a lot better than this visualization of the oil data. So these are supposed to be these different regimes of flow. One's laminar, one's annular, and one's turbulent. But actually, when you look at good visualizations of the oil data, these things are easy to model. All the structure is in the blue, and it's failed to capture that utterly. If you look at visualizations using the GPLVM, you get loads of structure out of that. Gene expression data, I can't even remember what the squares represent, but they're supposed to collect the data. It doesn't work so well. This is the visualization of, I like this. We used to generate speech from this, of different speakers, many of whom are still in Sheffield, looking at the parameters the HMMs used to generate their accents. This is James, who's left now. He's from the West Indies. He had a rich West Indies accent, anglicised a bit. And this is a guy from Glasgow. So they're sort of separate. That's me. That's my colleague Martin Cook. These are female speakers. They all move up to one side because we haven't removed pitch. The interesting thing is here, these are support staff who have South Yorkshire accents, and they come close together. So, in fact, they not just have South, they come from the same village. So you can sort of visualize South Yorkshire, another one's up there. So not brilliant, but you can sort of visualize using these sort of things. So the ISOMAP is just the multidimensional scaling on the shortest path approximation of geodesic distance. So we think of geodesic distance as the real distance that you would have to go around through the data, but they use this shortest path approximation. Just like in that roadmap example, eigenvalues can be negative. So it's not a Euclidean distance. But I think that may be a good thing, actually. One of the later algorithms, maximum variance unfolding, imposes Euclidean nature on this form. Actually, there's papers that say it's basically ISOMAP plus Euclidean constraint. I haven't read those papers in detail. I've spoken to the people who wrote them. That's really interesting if they're trying to do ISOMAP, if you can show it sort of like ISOMAP plus an additional constraint. Because I find it's a good algorithm, but it typically, I don't think it does quite as well as maximum variance unfolding. So Laplacian eigenmaps is a spectral method introduced in 2003, so 2 years after the first one. I mention it now because it's easier to explain than locally linear embedding. And all you do in this one is you define a neighborhood in the data space, you find that graph structure we talked about, and then you define a sparse adjacency matrix A, where that adjacency matrix is non-zero if 2 points are neighbors in that graph. They then argue that a good one-dimensional embedding is one where this objective function is minimized, where this objective function is e to the x, such that you're including 2 points xi and xj in the objective function if they're adjacent in the neighborhood graph. So it's sort of a non-weighted sum, which if we write in this form, with Euclidean distance between 2 data points like that, we can just turn it into our delta ij, the actual distance of 2 points in latent space. So they then convert that into matrix form, and they rewrite that by introducing the graph Laplacian. Now, this is a trick that I think, can't remember if I've got slides on it later on. It's a cool trick. It's used in, are people familiar with stiffness matrices? I've got something on stiffness matrices to try and illustrate this trick better a bit later on. But if you've got square distances between, if you ever something of the form, and it's a trick that I use in maximum entropy unfolding, so I'm pretty certain I've got something later on about it. If you're ever given something of the form, so this is the energy of a set of springs, as I'll show it later. So if the location of each spring is xi and xj, then kij, like this squared, the sum of that is the energy of the system, right? The displacement times the spring constant. Now you can rewrite this, and it's in my papers, and I may cover it, I can't remember if I cover it a bit later. You can actually rewrite this as L XX transpose trace. This is a nice rewriting because it's putting things into things that look a little bit more like Gaussian models, and it's going to be critical for some of the stuff we do. The reason this matrix L is known as the graph Laplacian, and Lij is equal to K minus Kij, and Lii is equal to the sum over J of the Kij's. So that implies that L1 has a null space. So they form the graph Laplacian. They don't introduce it in this way. I think it's as natural as a stiffness matrix, actually, personally. But they don't introduce it in this way. But they talk about it like this. Now, what they've now got is, to me, an energy system of a set of springs which are all connected to each other. So just like we saw in before, what they're sort of doing is they're saying, well, and I think I have this later on, they're saying that this system is a spring system of stuff that's all connected to each other. If you look at work on systems like that, this matrix, this Laplacian matrix, is known as the stiffness matrix. I mean, I think it's even in Wikipedia, actually. So it's funny, you don't see it in the machine learning literature much, but they talk about it as the heat equation, and they put a lot of physical stuff in as the heat equation. I think it's called the stiffness matrix. It's a while since I looked at Wikipedia. Oh, I can't see it. Wikipedia's changed. How dare it change? Stiffness matrix for other problem. Yeah. Oh, I think you don't even find much if you search for Laplacian stiffness matrix. Laplacian matrix. Yeah, this is the Laplacian that we're looking at. But it did say. Can you see the stiffness in there? See also stiffness matrix. There you go. Told you, but look, it's not very clear in here. It is the stiffness matrix as well. How frustrating. The maths is in my papers, so I don't really want to go through it. It's on the MEU paper to show that what you're actually writing down is the energy of this spring system. And what you do when you're doing the eigendecomposition on it, you're looking for the principal modes of oscillation of the spring system. That's not how we think of it in the Laplacian eigenmap system, but it's sort of one way of looking at it. What they say is, let's minimize that objective, but constrain this. Now, this constraint is slightly different to the things we've seen before. If you put this D in, you get a slightly different algorithm. You get the eigenvalues of a different object. It's a generalized eigenvalue problem. Our eigenvalue problem would be recovered if you didn't put that D in the middle, but it's very closely related. But what's going on, actually, is the eigenvalue problem you solve. This trace here, it gives you, this result of this is, the ones you want to retain for X are the smallest eigenvalues of L, not the largest eigenvalues of L. If these are the eigenvectors X, yeah, then they're going to rotate L around, and the trace is the sum of the eigenvalues. So you don't want the largest, you're trying to minimize this spring energy of this system. And so the result is actually you retain the smallest eigenvalues, which is opposite to what we've been doing. This Laplacian, though, the structure of this Laplacian it's a sparse matrix. It has zeros everywhere where xi and xj aren't connected in the neighborhood graph. But it's sort of clear that the eigenvalue problem you're actually solving is a little bit difficult, is, where's my slide gone? So, let me just write that on the board. The minimum eigenvalues of L are the maximum eigenvalues of K if K is equal to L inverse. Slightly awkward because L doesn't quite invert. But if you add a little bit of diagonal to L, because L has a null space in that object there, and you define K to be equal to that, the eigenvectors of this, the principal eigenvectors of that, are the smallest eigenvectors of this. Now, this algorithm is strikingly similar to PageRank as well, because PageRank is just doing this, but with pages, well, used to be, I mean, I'm sure it's nothing to do with the original PageRank algorithm, was just connecting web pages in a sparse structure and then looking at the largest eigenvector and then ranking according to the largest eigenvector. You can do that across millions and millions and millions of web pages because you can compute the smallest eigenvector of a sparse matrix. If the first thing you do is invert a matrix, if you invert the World Wide Web, and then you take the largest eigenvalue of the World Wide Web, you should be shot. Algorithmically, it's very clear that you should never represent the thing in this form, and you get a much faster. These algorithms, the Laplacian eigenmaps is like the fastest algorithm of any we'll show. It's super, super fast and can be applied to very, very large data as a result. Very trivially, because you can do these sparse eigenvector extraction problems. But you've got exactly the same interpretation of what's going on before, only now this K matrix here is this. So actually representing the implied square distance matrix, you're finding a delta, which is trying to approximate this in the L1 sense, this inverse here. You've not done anything to fit the parameters of L. You're just saying the parameters are 1 if people are neighbors, otherwise they're 0. But you're approximating something you never observe because you never compute this inverse. So it's a really elegant algorithmic trick, but the model itself you can see as being a Gaussian model in the way we thought of it before. I mean, it's not the only way. I'm sure that Misha Belkin, who worked extensively on this, I actually was at Berkeley visiting with him at the same time, about 2003, which got me into this stuff. And I'm sure he might disagree with this as the model, but it's a model that's consistent with the model for things we've talked about before. It doesn't do such a great job on say, the walking data. So now that the main structure in that data is the person taking the stride, and it pushes that into the third dimension. So actually, in terms of what we would expect to see in this, it's not doing such a good job. It's pushed that down. It has the fact that the start of the walk is crouched like that. But after that, I think it doesn't do that well. I think where this algorithm is really good, and I've never used it because in that domain, is I think with massive data. I think it matters far less what the parameters of K are in massive data sets than with... if you've got a massive data set, you can apply this algorithm very quickly. And I think the fact that you're just doing this coarse thing of saying the entry in the matrix is 1 if they're neighbors and 0 otherwise is really good in that high dimensions, because things start getting densely covered. The oil data, you start seeing the structure, the blue is separate. So actually this is somehow better than the previous one, but I think it's kind of coincidence. It needs more than 2 dimensions. It's known that the oil data is 2-dimensional. It's intrinsically 2-dimensional because it's artificially generated. But it can't recover that, and it's actually doing a worse job at separating the 2 main regimes than PCA does in 2 dimensions. 5 minutes. Okay. Locally linear embeddings. They start in this really interesting way. They say, well, let me try and reconstruct every data point by a weighted sum of its neighbors. So it seems like a totally different thing, and it makes sense because you're saying, I want local linear patches. Every data point should be reconstructed by its neighbors in this way. And so I'm going to basically minimize this squared error. But if I just do that, it turns out I don't get translation invariance and rotation invariance. So they point out this, and they say, actually, in order to do this, I have to constrain the sum of the weights, the reconstruction weights, to be equal to 1. The reason that sum does nice things is when you operate on this and you look at translations and rotation invariances, you start discovering that this whole objective doesn't mind if you rotate y or translate y. Okay? Which makes sense. So they sort of notice that, so they constrain that w, the sum of w's, to be 1. W's can be negative, but the sum must be 1. That's the objective function. This is just the description of that. Now that objective function can be rewritten. It can be rewritten by pulling the m's, doing exactly the same things we just did with the where I'm not again going through the details, but it can be rewritten with defining a matrix M to be Mij is equal to Wij if it's off diagonal, and Mii is equal to the sum of Wij's over J. Sorry. It doesn't matter which of these is negative. That can be negative or that can be negative, because M itself is not a symmetric matrix. So LLE, there can be your neighbors, one point's neighbors is not the same. Like if I'm a neighbor of you, you're not necessarily a neighbor of me. Every other algorithm in this class, you have to be bijective in the neighborhood. So M itself is not symmetric. But in the algorithm, when you look at that objective, this is the form of the objective. M transpose. Now, I'm short on time, so the punchline on that is that they then say, take the minimum eigenvalues of this. M transpose. But M itself has an interpretation. If L equals M transpose, just as this object here, through definition, L has a null space in 1, M transpose has a null space in 1. So M transpose, which is formed of all these W's, which are the parameters you fit locally, is also a Laplacian. So it's just a different way of parameterizing the Laplacian. And it's a sparse inverse covariance matrix again, with independence across the data dimensions. These are visualizations with LLE. It doesn't do such a good job on these things. Just as I think LLE has particular. I would use like isomap, or I would use Laplacian eigenmaps, depending on the scale of my data set. It's faster than isomap, but it's slower than Laplacian eigenmaps. But it can still sort of give quite poor embeddings when you've got a few data points. So one of my motivations for getting into this is this work, Maximum Variance Unfolding, where they explicitly said we're going to learn a kernel to allow for dimensionality reduction. And they're much more explicit about what we're doing. In this case, they actually do a semi-definite program to fit. They say, I'm going to have a general class of kernel matrices K, but I'm going to constrain the elements of that such that my observed distances in my neighborhood constrain the observations. They're just explicit about this. They say, I want the observed distances in the neighborhood to match these elements in my kernel. So they're constraining specific elements of the kernel matrix by the observations, combining in this way. And because this is all linear on the kernel, then they just say, and the kernel itself must be positive definite. So it's like isomap, because actually isomap will recover the same feature on the effective kernel, but here there's an additional constraint to say it's positive definite. And that's why it's a semi-definite program. And once they've done that, then they just go through the same process, but here they develop a kernel matrix directly, like as in isomap, unlike Laplacian eigenmaps and locally linear embeddings. And this is the observation. This effect is weird. We didn't have that in isomap. And I think it's coming from the positive definite constraint. I don't know the details of why it comes. But we do get this nice structure here. Almost like as if there's sort of extra noise in the latent space. It's a bit funny. Now, I looked at all those and I thought, I can't write a paper on that because I was trying to unify them. And then it turned out the final thing that I really don't have too much time to show you is what happens if you just do it properly. You just do maximum likelihood on the model. So you say, I'm going to do a probabilistic model which is constrained to have the observed moments. So these are the distances I observed equal to the expected moments under that Gaussian density. Well, under any density. So you start by saying, I'm going to generate a density. This is known as maximum entropy methods. So in maximum entropy methods, you say, give me the maximum entropy density that shows these moments to be true. So if you say the moments I want to match are the square distances between neighboring points, and then you say, I'm going to do maximum entropy on that, your answer is that the correct distribution is a Gaussian density, it's a Gaussian random field. It's just the thing we started off in the first place. It says your density should be of this form, with a little sigma squared on here. It says that your density should be Gaussian with a Gauss-Markov random field as the covariance. And the form of that parameterization, L, is given by a Laplacian. Now, it's very closely related to maximum variance unfolding, because what you can look at it as is maximum entropy instead of variance. So maximum variance unfolding sort of says the motivation is along the lines of, well, I'm going to increase the variance of my latent data, blah, blah, blah. Here, you're not doing that. You're increasing the entropy, which means you lose the semi-definite embedding property. But what you get is a genuine probabilistic model. So this is the form of the probabilistic model. This is known as the base distribution. So in maximum entropy in continuous spaces, you don't actually maximize entropy, you minimize a KL divergence with respect to a base distribution. This is the covariance of the base distribution appearing here. But this is K. So K is inverse of L plus, sorry, this is K inverse, right? Because it's in the Gaussian form, this should be K inverse. So you see that these models are related to a probabilistic model, which under maximum entropy is a Gaussian density. And the nice thing about that, a lot of the same tricks apply, is that Gaussian density is independent across the p-dimensional space. And all these sort of things about, why do these models work in high dimensions and not so much in small dimensions, suddenly become obvious and clear. If you look at models that assume independence across high dimensional features, these models work very well if p is large and n is small. They're really good in that domain. The parameters are all well determined. The odd thing is that the number of parameters scales with the size of the neighborhood. Your parameters actually become the elements of L. If I make everything part of the neighborhood, I just recover PCA. So if I say all my parameters, if I do maximum likelihood, remember the original system I said then K would be YY transpose. If I say I want to fit this model to data, because that's what we do when you do maximum entropy, it says do maximum likelihood once you've got this structure. They're always equivalent. If I fit that model without constraints on L, I recover PCA. And I recover PCA in the form with the largest number of parameters associated with it. As I drop parameters in this model, it becomes more nonlinear, which is a bit unusual. But it's because it's got this independence across P. Sorry, that's not clear on that variant, because I've got the trace in there. It's clear in that variant. It's got the independence across P. The final solution is then it's got maximum likelihood. This is the key point. Maximum likelihood is consistent. As you increase data points, the parameters become better determined. This solution is opposite. As we increase data features, the parameters become better determined, which is weird. So it turns the large p small n problem on its head and gives you a blessing of dimensionality. So all these models turn out to be sparse assumptions on the covariance matrix of a Gaussian random field. It doesn't even need to be Gaussian on some interpretations. It's just a random field. They parameterize them in different ways. The maximum entropy unfolding thing I mentioned at the end just says do maximum likelihood. And they're all giving you dimensionality reduction. This is the probabilistic model, right? The probabilistic model says that all the data points are connected by springs, and this thing lives in a heat bath. So I think that's actually not a bad probabilistic model for dimensionality reduction. Think of a mattress you find on a dump. It's a low-dimensional thing embedded in a high-dimensional space. And then you're trying to, once you've got that structure, unpicking the thing, you then use the thing we talked about at the beginning, D1, matching delta 1 to D squared. Okay, so it's related to all those models. I've got slides on that, but I'm out of time. So you can read the papers where I actually go through the maths. So it turns out that LLE, you can actually relate to this model as well. So you can see LLE as, if you do a directed version of LLE, you recover maximum entropy unfolding. It's something I've explored a little. The maths is given there, and you can actually, I've got an algorithm online. It's a fast version of doing the fitting. That's it. I think I'll go to conclusions. Oh, sorry. Yeah, so the final thing I did have in was actually this thing. This is a GPLVM as well. It has the same form. I talked about that a little at the beginning. I'm over time. So even the GPLVM has the same form. Okay, so the conclusion is that there are three sort of separate stages that are in a lot of these algorithms in terms of build a neighborhood, parameterize the L, and then do the eigen decomposition on it. And it's sort of unclear where all these things are coming from. Every single paper motivates the algorithm in a totally different way. But if you take this probabilistic perspective and say, actually, I'm just trying to fit a particular structure of a Gaussian density, then you can see what you're doing from a consistent view. However, there is a good reason for doing it in the way they describe, because you get really good speed-ups by conflating these steps. Like Laplacian eigenmaps, if we would never come up with the Laplacian eigenmaps algorithm if we were just thinking from the Gaussian random field perspective. It just wouldn't happen. It comes from a totally different perspective, and it's a fast algorithm that works on massive, massive data. So to me, this is a lesson in sometimes thinking about the algorithm's good, and sometimes thinking about the model's good. So conflating the three steps can allow for much faster algorithms, and that's not obvious when you're deriving things from a probabilistic perspective. So you can get mixing steps 2 and 3 allows for speed ups by never computing the similarity matrix itself. You can still understand the algorithm, though, from the unifying perspective while exploiting the sort of computational shortcuts that take from these shortcuts. Okay, so that's it.